Anybody been to Iceland before? Anybody want to go to Iceland? Me, I want to go to Iceland. I follow too many really good photographers on Instagram in Iceland. Anybody? Here's what inevitably happens when you want to go somewhere, then you see somebody you know that's there, right? Doing what you want to be doing. We really want to go to Iceland. It hasn't happened yet. It's been on my bucket list for a couple of years now. But yeah, the first year I was like, I want to go here. I think there's going to be some good hiking here. I saw a family I know from our church. They're in Iceland, living it up. That's how it goes, right? Anyways, this is a really beautiful, one of my favorite waterfalls in the whole world. I say that, act like I know all the waterfalls. I don't, but this is just a really cool one. So anyways, there's lots of great terrain, great hiking. It's called the Skogafoss in Iceland. You can look it up, really huge. But this picture is also appropriate for chapter 8 because we're talking about gases, liquids, and solids, right? So you got all three in one picture here. Anyways, if you want to go to Iceland, email me, we can chat about it. States of matter. So gases, liquids, and solids. We are going to focus on, you're familiar with these. We've talked about how these things, matter can change between these states, these phases. We have common names for those. But we haven't really addressed, a little bit we've addressed, indirectly we've addressed the level of energy. And then we're really going to dive into how these molecules and these phases interact with one another. And then the back half of chapter 8, second half of chapter 8, we're really just going to focus in on gases. How we study gases, how they behave, gas laws, all that kind of stuff. So looking at this figure, it's right from your textbook. I bet you can tell me which one's a gas, which one's a liquid, which one's a solid. First off, which one's a gas? A, B, or C? Yep, A. So we'll label it gas. B then is the liquid, and C is a solid. All right, so you can see differences in how these molecules are arranged. But what I really want to talk about is how much energy these have. So which state of matter, from looking at the picture, which one looks like it has the highest amounts of energy, the molecules in the picture? Yeah, the gas, okay? So we're actually going to write that. Highest, and they're moving, so it's kinetic. I'm going to write kinetic energy. I equate this to cars on the interstate. They're just zooming past one another, right? Don't have time to talk. They're flying. All right, liquids in the middle. So these are moving. So they have some kinetic energy. Not as much. Oops. Not as much as molecules in a gas state, but they're still moving, okay? Now in a solid, these molecules do have energy, just not a lot. They're just more like vibrating in place, okay? They're connected to each other. They're not really moving around the way they are in the liquid or the gas form. So we'll say lowest amounts of kinetic energy. All right, so that's a little bit about the energy association with these phases. So keep that in the back of your mind. Another thing I want to talk about, though, is the level of interaction between the molecules, okay? So if we equate these to gas particles are like cars driving on an interstate. Liquid molecules in a liquid, those might be like cars driving through the neighborhood, okay? They're a little bit slower, but they're still not stationary. And then solid is, I don't know, you're sitting at home or you're sitting in your front yard, okay? So which particles can interact the most? Which particles, which molecules do you think have the highest amounts of interaction between the two molecules? These are the chapter 8 notes, by the way, from the chat. Kendall says C. That's right. So these have the highest. I'm going to use the abbreviation IMF, Intermolecular Forces. I'll write it out this first time. Okay, IMF. These just mean these molecules are interacting the most, right? If you're sitting in your front yard, you can talk to your neighbor across the street. You can talk to your people, other people in your front yard, people on your street, people at your apartment complex. Some kinetic energy, though. Liquids, obviously, these have some. I'm just going to write some because it's kind of the middle of the road. Some intermolecular forces. Not as much as solids, molecules in solids, but less than molecules in the gas. Obviously, if you're flying down the interstate, you don't have time to interact with anybody, okay, unless they're in the car with you. So these have the lowest level of intermolecular forces, all right? So there's trends here, obviously. I want you to keep these, like I said, the energy association and the forces at play between molecules in the back of your mind and how they're associated with these phases of matter. Now I want to switch over here to this other figure and talk about this. So you see these common names: melting, freezing, vaporization, condensation, and these describe transitions between gases, liquids, and solids, right? But you also see these phrases in parentheses just beneath now. Because we know every reaction, every process is endothermic or exothermic. Okay, endothermic in one direction, exothermic in the opposite direction. So somebody remind me, you see heat released or heat absorbed. I want to write these up here. If heat is being released, is this endothermic or exothermic? I'm seeing it in the chat already, exo. Does that mean it's a positive or a negative delta H? Negative, okay, negative delta H. So let's go in and just label those, negative delta H on everything where it says heat is released. This is an exo, these are all exothermic processes. So vice versa, let me come back up. If heat is being absorbed, then this must be endo. And this is a positive delta H. So you can actually label all these processes. You can now label a change in enthalpy for all of these common processes. Positive delta H. Okay, so if I ask you on a quiz or on an exam, I say, here's a process, or I describe a process, and I ask you what kind of reaction this is, exothermic or endothermic, or I ask you about the sign on delta H, you should be able to look at this figure and tell me for any of these common processes, okay? Questions so far? Okay, now we're gonna really focus in on intermolecular forces. We're gonna look at 3 specific kinds. We're gonna talk about, and maybe you've heard of these before. So there's the same figure we saw, gases, liquids, and solids. In between each state of matter, there's intermolecular forces at play to varying degrees. The 3 types we're gonna talk about, the first one is van der Waals. They're also known as London dispersion forces. These are the weakest kind of intermolecular force, okay? And again, we're talking about interactions not like a chemical bond between 2 atoms. We're talking about interactions between 2 molecules, okay? So like not a hydrogen and an oxygen in a molecule of water, but 2 water molecules interacting, okay? In between molecules. Another kind we're gonna talk about is dipole forces. And before I move on, so this molecule is a little bit, this force is a little bit stronger than your van der Waals or London dispersion forces. Anybody remember what a dipole is though? What is a dipole? When do we have dipoles on molecules? Oh no, they've forgotten everything. Just kidding. Some of you are like, yeah, spring break, I forgot it all. Okay, polar or non-polar, yep. Slight negative to determine something polar when they aren't symmetrical. See when an element's more electronegative. Yeah, this is all good. Y'all remember some. So a dipole, let's draw a molecule that would have a dipole. So for example, HCl. When you have 2 atoms bonded together and they're not identical, if they're identical atoms like carbon bonded to carbon, that's obviously non-polar. There's no difference in electronegativity there. But when you have different atoms, you have the potential, the opportunity for a polar bond to be at play. Hydrogen and chlorine, if you look at the electronegativity chart, this is a polar bond. When we have a polar bond, we can assign the partial positive, partial negative, remember? Which atom would be partial positive? Meaning it's electron poor. The electrons are pushed away from it towards the other atom. Yep, thank you, Bradley. Hydrogen, So that means chlorine is the partial negative. And chlorine, guess what, has all these lone pairs that I did not draw. So that's definitely all the electrons in the bond and on that chlorine. Remember, elements that are closer to fluorine, they're more electronegative. Okay, so when you have this, you can draw a dipole pointing towards the negative sign. And when that's the case, it's a permanent dipole. There's a permanent separation of charge. You would have a polar molecule. Those can experience dipole-dipole interactions. We're going to discuss that in detail in a few slides. Lastly, we're going to talk about hydrogen bonding. Right? Maybe some of you have heard of that one before as well. This one's a little more complicated. It's the strongest intermolecular force that we're going to talk about. And like I said, it's a little more complicated than the other two. But the next couple slides are actually out of order. So I'm going to skip over dipole for a second. I want to go straight to van der Waals. Down here. Okay, van der Waals forces occur in all molecules, whether you're polar, non-polar, if you can hydrogen bond or not, every single molecule experiences van der Waals or London dispersion forces. You'll hear me use these two names interchangeably. But it is dominant, it's the strongest intermolecular force in non-polar molecules. Okay, so molecules that cannot hydrogen bond and molecules that aren't polar overall, no dipole, then the strongest force is just the London dispersion or the van der Waals forces. Okay, so look at these pictures actually. Obviously, these molecules down here are polar, and these molecules up top are non-polar because they're not, my writing is really on point today, non-polar. Okay, they're not color-coded. There's no electron density map like these little rainbow molecules you see down here showing a separation of charge. So we got these non-polar molecules up top. So how do we get London dispersion forces in? What are they made of? What causes them? Well, that's this point. They're caused by interactions between temporary, or you could say momentary dipoles. And that sounds nuanced and confusing, and it is, okay? So what the heck is a temporary or a momentary dipole, okay? Well, it has to do with electrons, okay? Because a dipole is the separation of charge based on where the electrons are in the molecule. So we know every molecule, every bond, that's where electrons are. So there's electrons right here, right? Now we draw them sitting nice and neat in the bond, but are electrons ever like still? Are they ever static? Yeah, like my 2-year-old, she's never still because she's all over the place. She nearly fell out of our chair on the patio. And I was like, great, right before Easter, you would have a huge scar on your forehead. They're never still, okay? They're always moving, literally. You could draw them like this. They're just always back and forth everywhere in the molecule. So at any given time, if you took a snapshot of this molecule, the electrons might be over here, or they might be on the other side, or they might be split on two sides. But let's just say, they're both on one side. Then for just a split second, it's true that this side is the partial negative and this side is the partial positive. But again, this is momentary. It's there and then it's gone, okay? And what if it happens on the other molecule, okay? What if for just a moment you have the same sort of separation of charges? This can happen if they're moving infinitely all the time. You could have it set up like this. And when you have something like this, that is where the partial positive and then the partial negative would see each other and be attracted for just a moment. Now, for a single two molecules, a single bond in between molecules, or interaction, I should say, not bond, it doesn't sound like a big deal, not very significant. But let's say you have millions and millions of molecules, and these are happening all the time, and they're there and then they're gone. They do add up, and they do affect things like boiling points and melting points. We're going to see how these affect boiling points and melting points, okay? So that's a temporary dipole, all right? So another thing to know is that larger atoms, it makes sense that larger atoms, they have more electrons, more protons, more electrons. And therefore, if you have more electrons, those electrons can fluctuate more, okay? And the more London dispersion interactions can happen from more fluctuation, okay? Also larger molecules with, molecules with a larger surface area will also have more London dispersion force. So the more electrons you have, the bigger your atom is, the farther you travel down the periodic table, the more London dispersion forces can happen. You'll tend to have molecules that have higher boiling points and melting points. And then the more surface area a molecule has, the more London dispersion forces or van der Waals forces that it can experience. An example for that is right down here. Let's look at these two molecules. We got pentane, which is the common name for this carbohydrate. And then we got this other weirdly named thing, 2,2-dimethylpropane. Look at these. How many carbons and how many hydrogens are on each of these? Look at the Lewis structures. It's actually identical. Same number of carbons, same hydrogens. So I'm going to write what I call the empirical formula. I'm just going to write how many carbons and how many hydrogens. How many do we have? You can count them. It should be C5. Yep, 5 carbons. How many hydrogens we got? Yep, so C5H12. And that's for both of them. So the same empirical formula. And they look different though. Their Lewis structures are different because we know there's multiple ways you can draw things sometimes. So what I noticed about which one looks like it has the larger surface area? Pentane or the 2,2-dimethylpropane? Yeah, I agree. Pentane. It's elongated. Okay, the carbons are put all in one chain. So you have more surface area. The 2,2-dimethylpropane just kind of looks like it's all wadded up if you're looking at the spherical space filling model of it. So this one has a larger surface area, and this one has smaller surface area. Okay, so why is this a big deal? Well, now let's look at the other piece of information given down by the name. It says BP equals 36, BP equals 9.5. And it's a temperature, obviously, because it has units of degrees Celsius. This is the boiling point for these molecules. If I had a cup full of pentane or 2,2-dimethylpropane, which one would boil first? The one that would boil first is the one with the lower boiling point. Okay, it takes less energy or less heat. We know heat is energy, form of energy, to boil 2,2-dimethylpropane. Why is that? Because it has a smaller surface area. The larger the surface area, the larger the potential opportunity for, sorry, everyone. That's frustrating. The larger the potential for London dispersion forces to happen, okay? So I just wanted to point that out. It does affect real properties like melting points and boiling points, okay? All right, any questions so far on van der Waals? That's kind of it for van der Waals. How they happen, how they affect different molecules. All right, now we're gonna go to dipole interactions, okay? So I'm actually gonna scroll up because we passed over this slide earlier. All right, these are molecules that are polar, experience dipole-dipole interactions, or have a permanent dipole. So we got a figure of this right here, and you see the color-coded regions, and you can see how neighboring molecules would orient themselves. You see the partial positive and negative signs on the molecules, and so the interaction happens here. There's attraction between positive and negative, right? Opposites attract. So there'd be a dipole-dipole interaction there, and there'd be dipole-dipole interaction there. There'd also be dipole-dipole interactions here and dipole-dipole interactions here, right? Anywhere you have the partial positive and negative lined up. So that's a little bit of how it looks. What's happening, obviously what we've kind of boxed in is that the positive pole of one molecule is attracted to the negative pole of another. And these are stronger than London dispersion forces, but they are weaker than hydrogen bonding. Okay. Now, this figure as well in the bottom corner here is from your textbook. And we have, again, two different molecules. One is polar, one is nonpolar. So we got butane, C4H10 on the left, and we got acetone. If anybody's ever used like fingernail polish remover before, that's acetone is in that. C3H6O. Okay, now what's interesting, look at this down here. The molecular weight for both of these is the exact same. They're different molecules, obviously different Lewis structures, different atoms involved, but they weigh the same. So essentially we could say they're the same size, right? According to their weight. But also then the piece of information below that, their boiling points are drastically different, a difference of 50 degrees Celsius. That's a huge Huge difference, okay? 21 degrees Celsius is room temperature. 71 degrees Celsius, I don't want to ever experience that temperature, okay? It's insanely hot. So the boiling point between these two molecules, even though they're the same size, is drastically different. Why is that? It's because one is nonpolar. How do I know butane is nonpolar? Anybody? Why am I saying butane's not polar? Yes, the color coding is different. It's all just green. We don't see a red region, but that's not exactly why. Look at the kind of bonds. All we have are carbon-hydrogen bonds and then carbon-carbon bonds. We know carbon-carbon bonds are nonpolar. Carbon-hydrogen bonds are also never polar, okay? So the whole molecule is made up of bonds that are not polar, okay? Yeah, and if you drew it out, the Lewis structure, I know you got different angles here, but it is symmetrical as well. But none of the bonds are polar, so that's why overall it's nonpolar. But we do have polar bonds here. We see a separation of charge on the carbon and the oxygen. So we got a dipole. We can literally draw that in, right? So because of, and we got lone pairs on this oxygen, all right? So there's definitely a lot of electron density there on the oxygen. Oxygen's very close to fluorine on the periodic table, very electronegative. So because of that, if we had a neighboring molecule of another acetone, they would orient themselves just like you see up here with the red and the blue regions, okay? And you get a ton of dipoles interactions across these molecules of acetone. And it's because of that reason, because these are polar molecules, it takes a lot more energy, a lot more heat to break apart all these molecules to get them to melt or to boil or to change phases, okay? So that's why the boiling point is like 50 degrees higher. So that's dipole in a nutshell, and that's van der Waal in a nutshell. Questions so far? Okay, I know it sounds straightforward, but we're gonna work a practice problem in a bit to make sure we really understand everything, because we wanna be able to look at a molecule and know what kind of interaction it would experience. Last one we're gonna talk about is hydrogen bonding. Hydrogen bonding is the strongest, so we say it's the king of all intermolecular forces. And interesting enough, this is not a false statement. It's responsible for why we have water, or I should say life on Earth. We couldn't have life without liquid water. So hydrogen bonding is the reason water is a liquid at livable temperatures. Obviously, if you go like the North or South Pole, we don't necessarily consider those to be livable temperatures. But at livable temperatures, hydrogen bonding is the reason we have liquid water. It's the strongest, stronger than van der Waals, stronger than dipole forces. And here's the actual definition of it, okay? It occurs between the lone pair, specifically on 3 different atoms, either an oxygen, a nitrogen, or a fluorine, okay? I know there are other atoms with lone pairs, chlorine, bromine, phosphorus, sulfur, but we're not talking about those atoms. We're just talking about oxygen, nitrogen, fluorine. So it occurs between the lone pair on those atoms and what we call a positively polarized hydrogen. What is a positively polarized hydrogen? It's just a hydrogen that has the partial positive on it. It's a hydrogen in a polar bond. That is a positively polarized hydrogen. Okay, and that hydrogen must be bonded to, it must be made polar because it is bonded to a oxygen, nitrogen, or fluorine. All right, so we're gonna define this a little bit more. We're gonna draw some stuff out, make some other statements about it on the next slide, but look at DNA. Our DNA is actually held together by hydrogen bonds. I'm gonna point this out. So here's the structure of DNA. We know it's a helix. So we kind of got the Lewis structure of all the DNA bases outlined on this helix. And you see something when you zoom in really close, you see all these little dotted lines, okay? And they're specifically around oxygens and hydrogens. I'm gonna just box some of them in. There's a lot of them. All of these are hydrogen bonds and they're holding your DNA together. That is because all of these hydrogens, we could literally go draw in, all of these hydrogens are positively polarized. Okay, and all of these oxygens have these lone pairs and they're partial negatives. So I should do a different color. Partial negative, partial negative, partial negative, okay? You could draw that in on all of them. Now these dotted lines, like right here, this is not a hydrogen bond. This is just kind of trying to indicate a third dimension, like the atom is pointing backwards out of the plane of the slide. But the ones we boxed in, these are hydrogen bonds. So you can see it's important for DNA. Proteins are held together with hydrogen bonds. If you look at a sea of water molecules, I mean, it just looks like a spider web almost. So just held together, tons and tons of hydrogen bonds between all the molecules, okay? So they're important. And specifically, let's look at two molecules that they're really, really important for, water and ammonia. So we got water. Oh. Okay, ammonia, not ammonium, right? So I want to zoom in on water for a second. We got these two water molecules. The red is the oxygen, and the white spheres are the hydrogens, and then we have the Lewis structures up above. And we see that they're oriented a certain way. And I'm going to label the two parts. So the dotted line in between this hydrogen and oxygen, that is the hydrogen bond. The hydrogen is positively polarized because it is bonded to this other oxygen, okay? But any other because it's got this partial positive, it sees the partial negative on the oxygen of a neighboring water molecule, and there's attraction there. That's the hydrogen bond, okay? So we call the hydrogen, by the way, we label these parts. We call the hydrogen a donor. Okay, it is donating that positive charge to the oxygen that is attracted to it, okay? And we call the lone pairs on the oxygen an acceptor. All right, it's accepting that. So donor and acceptor. So a hydrogen bond has to have two components, a donor and an acceptor, okay? Now we have other donors and acceptors on each water molecule that we've not labeled. Any hydrogen that is positively polarized could be a donor. So how many donors do you see just in this figure right here? We've only labeled one. But there's more. Will the hydrogen always be the donor, Bailey? Yes, hydrogen will always be the donor. So yep, I'm seeing in the chat there's 4. That's a donor. This hydrogen is also positively polarized, even though we haven't labeled it. And these are bonded to oxygen, so they're also positively polarized. So there's 4 donors total. Each one could participate in its own unique hydrogen bond with another water molecule. Okay, so imagine it could get pretty complicated pretty quick. Any lone pair, the lone pair specifically is what the acceptor is. So this lone pair right here, that would be an acceptor. The lone pairs over here on this oxygen, these would both be acceptors. So any of these acceptors could, Sterling says, what is O accepting? It is accepting this positive charge from the hydrogen, okay? There's an attraction, electrical attraction because separation of charge. So it's accepting that positive charge. So we call them acceptors. So any of these lone pairs could also participate in its own unique individual hydrogen bond. Okay, so how many hydrogen bonds could we get total? You just add up the total number of donors and acceptors. You could literally have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen bonds just between, or just with these 2 water molecules. And if you added other water molecules, you could have more. Okay, what about ammonia? We've shown 1 hydrogen bond. Okay, let's label the parts. Obviously the hydrogen here is, hydrogen's always the donor. And the nitrogen is more electronegative than the hydrogen, so it's the partial negative, and the lone pair there is the acceptor. But how many donors and acceptors do we have? Any hydrogen, this hydrogen, any hydrogen that's positively polarized, all of these hydrogens, okay? These would all be donors. So between these 2 molecules, you've got 6 donors, 6 hydrogens, and you got 2 lone pairs on the nitrogens, 2 acceptors, okay? So again, you could have another 8 individual hydrogen bonds from all of these donors and acceptors. Okay, anybody confused? Seeing some interesting looks. Questions on this? Keegan says, I don't see 8. No, you don't. We haven't labeled all 8. We've just shown 1 individual hydrogen bond. I'm just saying, literally, this hydrogen right here, it could hydrogen bond if we had another neighboring molecule that came up, like if we had another nitrogen, another ammonia. Okay, that one could hydrogen bond there. this water molecule could also form a hydrogen, or sorry, not water molecule. This positively polarized hydrogen could form another hydrogen bond with a neighboring molecule, okay? It could, I'm just saying it could, we haven't shown it. So we could get a hydrogen bond there. We could get a hydrogen bond with that donor. We could get a hydrogen bond with that acceptor. We already see one hydrogen bond here, but then we could also have individual hydrogen bonds with all these other donors, okay? So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Well, this one is 1 right here. So if you wanted to say 7, but you have 8 things that could hydrogen bond. Does that make sense? Yeah, Mackenzie, only 2 acceptors. All right, we're going to talk about it some more and define a few more things. Maybe it'll click in. I'm doing all this and I'm going into this detail because you're going to have a hydrogen bonding lab after exam 3, and you're going to have to look at a molecule and tell me how many acceptors, how many donors, how many hydrogen bonds could you get. So you just add up the total donors and acceptors and tell me total how many hydrogen bonds you could have. All right, I want to make some statements though, because there's 2 parts that are necessary on a molecule for it to hydrogen bond in pure form, okay? Sometimes molecules don't have both parts. Maybe they only have 1 part. Maybe they only have a donor and they don't have an acceptor, or vice versa. So can those hydrogen bond? Well, let's talk about it. So here's what I want to say. I want to make this statement. Molecules with both donor and acceptors can hydrogen bond in pure, I should say pure form, okay? Meaning with another molecule identical to itself. That's what I mean when I say pure form. It can hydrogen bond with another molecule identical to itself. So examples of that we just saw. Water is an example of that. Water has both a donor and acceptor. Ammonia, okay? Let's say you have this acid right here, HF, hydrofluoric acid. This is an example of a molecule that has a donor and an acceptor. Could you label them? I bet you could. All right, so they can hydrogen bond with molecules identical to themselves. But molecules with donor or an acceptor can hydrogen bond, but not with itself, okay? It has to hydrogen bond with a molecule that's providing the missing piece. So let's look at an example. If a molecule, what about a molecule like this? HCl. Okay, this hydrogen right here. Now I know I don't have an electronegativity chart. I think I actually have one down here. I'm gonna scroll down to the electronegativity chart. We got hydrogen 2.1 and chlorine 3.0. So this is definitely a polar bond, and this hydrogen is definitely positively polarized. So we could draw that in, right? But we don't have an oxygen, nitrogen, or fluorine in this molecule, okay? So this molecule could hydrogen bond with, say, a water molecule, right? But it cannot hydrogen bond with another molecule of HCl. So it could hydrogen bond with a water molecule if we had an oxygen. Sure, you could get a hydrogen bond right here between that hydrogen and the lone pair on the oxygen. But it can't hydrogen bond with another HCl molecule. Does that make sense? Another example, what if we had a carbon that was like double bonded to an oxygen and then had 2 hydrogens like this. These hydrogens are not positively polarized because those carbon hydrogen bonds are not polar. But we do have these lone pairs, these are acceptors. Okay, over here we had a donor. So if it has a donor or an acceptor, it can hydrogen bond, just not with itself. Does that make sense? Not in pure form. Okay, I just wanted to make that little distinction. Questions on this? I told you hydrogen bonding is the most complicated.
Okay, so like, how do you know like how many donors or receptors there are?
You have to be able to identify if a hydrogen is positively polarized or not. Okay, so you gotta, I'm gonna give you this electronegativity chart on the exam. You gotta be able to count positively polarized hydrogens. I'm not counting these hydrogens. These are not positively polarized because they're not in polar bonds. Only hydrogens that are part of polar bonds. And then you also have to be able to count acceptors. Lone pairs are acceptors. So here's another one. Okay. So that's how you count them. Lone pairs on an oxygen, nitrogen, or fluorine. Look at this definition up here, Kishan, right there. Or positively polarized hydrogens. These could all contribute or make hydrogen bonds. Does that make sense? In the chat. So it could make a water molecule off of those acceptors, but not just another molecule like the one that was drawn. Yeah, that's correct, Bailey. I'm assuming that you're talking about this CO, CH2O molecule down here. Okay, so let's actually put this into practice. I want to see how all this landed with you guys. Okay, what characteristic must a compound have to experience the following intermolecular forces? Hold on, back to the chat. I'm confused on how those hydrogens are not polar. Well, if you calculate the electronegativity difference between carbon and hydrogen from a chart, Keegan, it's a difference of 0.4. Okay, to be polar, it has to be greater than 0.5, or I should say 0.5. Oh, I ran out of it. 0.5 or greater. Okay, that makes sense? All right. I'm talking about the electronegativity difference there. Can I take your slides? Use? Is this the slide you want? Sorry, I had a question in the chat.
The next slide, like above it.
Okay, right here. So we're gonna do a practice problem, and I'm gonna run a poll question after this. All right. So what characteristic for a compound to experience the following intermolecular forces? I kind of want to edit this question. For these forces to be the strongest, what kind of molecule do you need to be? So to have London dispersion or van der Waals forces, and that's the strongest intermolecular force you experience between a neighboring molecule, what kind of molecule would you be? Yes, Keegan. So Bailey, yes, all molecules experience them, but not for all molecules are London dispersion forces the strongest force at play. It's just for nonpolar molecules. Okay, London dispersion forces are the strongest force for nonpolar molecules. Okay, but yes, all molecules do experience them. All right, what about dipole-dipole? Okay, you're what kind of molecule if dipole-dipole forces are the strongest thing you experience?
Polar.
Yeah, polar. Danielle, yes. Okay. What kind of molecule are, I'm gonna reword the question. What kind of molecule are you for these interactions to be the dominant or strongest intermolecular force you experience? Okay. Hopefully that helps. So if you can hydrogen bond, what kind of molecule are you? You have to have two characteristics, and they're specific. What kind of things do you have? What kind of characteristics do you have? Lone pairs on what? Okay, lone pairs, not just on anything. Yeah, very specific. It's lone pairs on oxygen, nitrogen, and fluorine. Okay, not lone pairs on a chlorine, not lone pairs on a sulfur. So lone pairs on these, and then what else? So yeah, Autumn said a donor and acceptor. You can tell me donor acceptor, but you better know what you mean when you say donor acceptor. Summer says a positively polarized hydrogen. So I'm just gonna draw this. Okay, you gotta have those two things, those characteristics. Okay, good. All right. This is the kind of problem I want you to know how to do for the exam. Identify the predominant or just the dominant intermolecular force in these following molecules. Okay, we're talking about these molecules with another identical molecule, so in pure form. So if we have nitrogen, the way you do these is you first draw out the Lewis structure. See what kind of molecule you're dealing with. Decide, is it nonpolar, polar, or does it have the requirements for hydrogen bonding? The easiest way, again, I encourage you to do this, is draw out the Lewis structure. So if we had two molecules of nitrogen, what kind of intermolecular force would they experience? London dispersion, obviously, but is that the strongest one they will experience? Well, could they experience a dipole interaction or hydrogen bond with each other? I'm not talking about with a molecule of water or anything like that. So here's what I notice. We do have lone pairs on a nitrogen, but again, it can't hydrogen bond because it doesn't have both. It doesn't even have a hydrogen in the molecule. It could hydrogen bond with water, but not between two molecules of nitrogen. So now we just need to decide. Tyler said they would be nonpolar, right? So van der Waals. I agree. Anytime you have bonds between two identical atoms, that's a nonpolar bond. So these bonds right here are nonpolar. So the type of intermolecular force between these would be London dispersion. Okay, or van der Waals is fine. Okay, so that's the strongest type of force that would exist between two molecules of nitrogen. All right, B, what about HCN? I'm gonna kind of slide over here and draw out HCN, looks like this. If you are still not confident in your ability to draw Lewis structures, this class is gonna be exponentially harder for you from now on, okay? So what kind of molecule is this? What kind of bonds do we have? Hydrogen-carbon bonds. We always say these are nonpolar. But what about the carbon-nitrogen bond? We need electronegativity chart. Carbon and nitrogen are right here. We got 2.5 and 3.0. So the electronegativity difference is 0.5. That's polar. 0.5 and above is polar. So we have a separation of charge, and we could literally draw in the partial positive and the partial negative. We give the partial negative to nitrogen because it's more electronegative. It's closer to fluorine. So we could draw a dipole in. Boom, right there. This is polar. And what I'm seeing in the chat is everybody is saying, yes, the kind of interaction that would sit between these two identical molecules, this would be dipole. Okay. You could draw it in on the other neighboring molecule as well. All right, questions here? We got one more and then I'm gonna poll question and let you do some. CCl4, I'm gonna draw it down here. CCl4. Okay, what do y'all think about this one? Carbon-chlorine bond. Is a carbon-chlorine bond polar? Carbon's 2.5, chlorine, looking at the chart, is 3.0. 2.5 and 3.0. So just like carbon nitrogen, these are polar bonds.
Don't they cancel out? Because it all kind of pulls away. So
they do. So it's true. This is partial positive and these are all partial negative. But when you draw the dipole in, look what happens. You got one pointing that way, one pointing that way. When they point opposite directions, they cancel. You've got one pointing to the left and one pointing to the right. When they're pointing opposite directions, they cancel, okay? So because of that, this molecule overall is non-polar. And the strongest type of intermolecular force molecules of CCl4 would have is London dispersion forces because of that. Or van der Waals, okay? Does this make sense how we're going about this? All right, you try. I'm gonna launch the poll now. These next three in red are yours. Here we go. So put your answers in. What's the strongest force for ammonia, CH3Cl, and CH3COOH? If you're not sure, draw out the Lewis structure and examine what kind of bonds you have. I'm gonna zoom out and let you see the electronegativity chart as well, in case you wanna calculate anything. One of these we've already talked about. If you were paying attention just a couple slides ago. I'm gonna start drawing the Lewis structures out. I'm gonna give you some more time though. Okay, so you should have Lewis structures that look like this, and then you start asking yourself, are these polar molecules? Are they non-polar? Do they have, can I identify a donor and an acceptor? Do they hydrogen bond? What's the strongest force? Just because, also too, just because you got polar bonds, remember, doesn't mean your molecule's polar overall if there's symmetry or if dipoles cancel. And just because you have hydrogens doesn't mean you have donors. You've got to be positively polarized in a polar bond. All right, I'm gonna give about 30 more seconds. So less than half of you have voted. Go ahead and throw some answers in if you're not sure. Okay, 10 more seconds. All right, I don't see the numbers going up, so let's look at these. What you guys said is right here. Okay, NH3, most of you said hydrogen bonding, but almost the other half of you chose the other options. So I don't know why we don't have 100% agreement on this one, because we already looked at ammonia a couple slides ago, right? As a prime example of a molecule that can hydrogen bond with itself. Right here, ammonia, NH3, hydrogen bond. So if you're paying attention on this slide, you should have picked hydrogen bonding for that. So we should have had 100% on this one. So this one, we've got donor, all of these hydrogens right here. Okay, these are all donors. And this lone pair on the nitrogen is an acceptor. That's the strongest intermolecular force, hydrogen bonding for this one. Okay, E, you've got CH3Cl. Well, we know carbon hydrogen bonds are never polar, but the carbon chlorine bond, if you looked at the electronegativity difference, that is polar. So you could draw in partial positive and partial negative. So you can draw a dipole in right there, doesn't cancel. So the strongest intermolecular force, most everybody, well, not most everybody, only 64% of you said that dipole. dipole forces are the strongest one it would experience. It's not London dispersion because this molecule is polar, and it's not hydrogen bonding because none of these hydrogens are donors. They're not positively polarized, and you don't have a lone pair on an oxygen, nitrogen, or fluorine. You do have lone pairs, but not on the atoms they need to be on. Okay, F, structure F, the popular answer was hydrogen bonding, and that's correct. Why? Because this hydrogen right here is bonded to an oxygen, nitrogen, or fluorine. Okay, so it is positively polarized. So it is a donor. And all of these lone pairs right here on the oxygens, these are all acceptors. So this can hydrogen bond with another molecule identical to itself. All right. Questions on that? I don't think these problems are super easy because there's a lot of steps. And Autumn just said, can you write out a list of steps to solve these? Yeah, real quick. Just gonna zoom in right here and do that. Number 1, draw Lewis structure. 2, identify, I'm gonna say ID if you have polar bonds or if you have a polar molecule. 3, also check for hydrogen bonding requirements. Okay. Also on part number 2, I would say if you have a polar molecule, draw the dipoles. And once you do those 3 things, then you should be able to decide what type of intermolecular force is the strongest. Okay. Okie doke. Take a screenshot of that, write it down. We're getting close to time. We got about 10 minutes left. So I'm gonna move on to a couple more things. This is a great practice problem. I'm not gonna do it right now. I'll do it in the review probably Monday. But if you want more practice, try to do that. So I'm asking 2 questions there. Which species or which molecule can hydrogen bond in pure form? So meaning with another identical molecule, or which one could hydrogen bond, just not with itself, but with a water molecule. So which one has donor and acceptor, or which ones just have one or the other? All right, this table right here is just a review of everything we've talked about on these 3 types of intermolecular forces, which one's the strongest, what the characteristics are. I'm skipping over this table right now. I usually point something out on it that's kind of cool, but I'm not gonna ask anything about it on the exam. Okay, so I wanna get to gases these last, 10 minutes we got. I'm just gonna introduce this concept and then we're gonna pick up with how do we study gases. We're really gonna look into a lot of different gas laws, which are equations, so there's gonna be math involved on Thursday. All right, so gases. How do we characterize gases? Well, there's 3 properties: pressure, volume, and temperature. These 3 properties allow us to predict a lot of things about the behavior of gases. I also have this picture over here. Anybody know what's in this picture? We've got these cylinders. It always kind of makes me nervous when I'm driving past like an 18-wheeler that's loaded with all these gas cylinders. So there's gas in all these cylinders, but why would this be somewhat dangerous? Why are these chained to the wall, in other words? And you see these fancy valves on the top. Flammable, you certainly do not ever want to put a flame near these things. You don't want to heat them up. Why? What is in these high pressure? Thank you, Glenna. These are pressurized gas cylinders, okay? So gas particles have a lot of space between them, right? Remember the picture for gas particles? That means you can force them together, okay? And the more you force them together, gas particles are moving around really fast, the more highly pressurized they'll be. So some of these gas cylinders can contain gases with up to like 2,000 pounds per square inch of pressure. And if they were to be heated up or if they were to bust, could probably blow through like a concrete wall. So That's why they make me a little nervous sometimes. But you'll see them a lot in research labs, hospitals sometimes when you deal with oxygen tanks. A helium tank, probably you've used that before to blow up balloons and stuff. But let's talk about pressure. So pressure is one of the properties we examine when we talk about gases. What is pressure? It is nothing more than a force per unit of area. You may be familiar with this when it comes to tire pressure, okay? Think about a tire. The gas inside collides with the walls, and that's what creates pressure on them. I never think about tire pressure. I'm always thankful for the people in my life that do, though. Anybody, when you're about to go on a trip, anytime I'm about to go on a trip, my dad's like, your tires look low. I need to air them up for you. I never think about these things, okay? My husband does. I don't. You do think about them, though, when you get a flat tire, I bet. That always sucks. Or when you run over something. Why are tires so dang expensive? But tire pressure is often measured in pounds per square inch. Okay, so pounds there would be the force, square inch is the area, and we abbreviate this PSI, right? So that's 1 unit of pressure. So I'm about to tell you some unfortunate news. There's like 6 or 7 different units for pressure. I don't know why there's so many. I didn't write them all. I just am delivering the news. We're going to look at several different units for pressure. Okay, so PSI will be a very common one. Anybody know what tire pressure should be, roughly?
Doesn't it vary per vehicle? Like mine's 35.
Oh, well, I don't know. I'm not that technical. I just know it should be like around 34. Okay.
Gotcha.
Yeah. But maybe it does. Okay, another unit for pressure. Atmospheres, okay? The air in the atmosphere above you puts pressure on you. I hate to deliver the news. You thought it was your chemistry class creating all the pressure that you feel from all the assignments and exams. It's not. I'm sorry. It's just the atmosphere. But 1 square inch of you, isn't this amazing? 14.7 pounds of pressure. Go pick up a 15-pound weight, okay? Now, we're just used to it because we live life that way. That's natural for us. But atmospheric pressure, 1 atm, is 14.7 pounds per square inch. That's a lot. So we have a relationship here. And we could convert between these units if we had to. 1 atm equals 14.7 psi. So if you had 2 atms, right, you would just double it. So you could do conversions with this kind of unit. So that's another unit, atmospheres and psi. Now this is at sea level, by the way. So fun news, we kind of got to go to Colorado for spring break and ski a little bit. We got to go on the Continental Divide. So up on the Continental Divide, we were 12,000 feet up. So obviously the atmospheric pressure, the higher in elevation that you climb, or if you fly in an airplane, is going to be a lot lower. But at sea level, it is 14.7 psi. But it changes with elevation. Okay, another unit of measure. I told you there's a lot. You're about to ask, who in the world just sat around and thought of different units of pressure to create? Who has that much time on their hands? Well, scientists do. So this one is actually more technical. There's a dish. It's a mercury-filled dish. There's mercury in this. Atmospheric pressure pushes down on the dish and it forces. Okay, thank you, Tyler. A lot of this is appropriate, I promise. But this one is a little interesting. Forces the mercury up the column, and they decided to measure this as a unit of pressure. Okay, so it went up the column 760 millimeters of mercury. So they literally created a unit out of that for pressure. I'm telling you, this is interesting. So it's sometimes called a torr based on the guy who invented this. So we have more relationships and more units of pressure. 760 millimeters of mercury. You actually may have heard of inches of mercury before. Sometimes people say inches instead of millimeters. But 760 millimeters of mercury is 1 torr, and that's just 1 atm. Don't worry, I'm not going to ask you to memorize all of these, only some. We got a few minutes left. I think that is kind of where I'm going to end today. Yeah, we'll pick up with these last units of pressure for gases the next day, and then we're going to get right into gas laws. Okay, so that's what's coming. So again, if you want to wait to try to attempt the bonus point opportunity until after Thursday, we'll talk a whole lot about gas laws, and we're going to work a lot of problems. Then great. That's where I'm going to pause for today. If there are any other questions about what we've gone over, pressure, units for pressure, intermolecular